Welcome, everyone. It's my great pleasure to announce the talk of Professor J.M. Landsberg, OM Professor of Mathematics at Texas A&M, on the topic of lower bound barriers in complexity theory and overcoming them with geometry. Please.
Great. So thanks so much, Matej, for the invitation. It's great to be back here at the Institute. I'll be giving two talks. This morning is kind of a broad overview and just touching on some recent progress. And then this afternoon, it'll be a chalk talk on work in progress. So sort of the two extremes for a lecture. So I didn't know who would show up, so I'll start in the beginning. In 1968, Strawson looked at the standard way we multiply matrices. Uses about n-cubed arithmetic operations to multiply n by n matrices. And since this algorithm had been around forever, he decided, well, let's at least prove it's the best possible algorithm. So how are you going to do that? Well, maybe let's just prove it for 2 by 2 matrices. But still, how can you write down every possible algorithm? So let's work over a finite field, and then you can actually write down all possible algorithms. And he failed. This is what he came up with. The only thing you need to see on this slide is an algorithm that multiplies two 2 by 2 matrices using 7 multiplications instead of 8. There's more additions, but let's not worry about that for now. Maybe the other thing to notice on the slide is the entries of the matrices need not be scalars. They could be elements of an algebra, for example, n by n matrices. So this algorithm actually scales up, and you can multiply large matrices using less multiplications. And in fact, the number of additions when you rescale also gets controlled. So you get down to 2 to the n to the 2.81 arithmetic operations. And then, of course, once you know you can do better, you want to know how much better can we do? And there was this amazing progress over the next 20 years that went down from n to the 2.81 to n to the 2.38. Now, there's a caveat here in that Strawson's algorithm is a very practical algorithm. It's actually more efficient than the standard algorithm when your matrices are of a size about 1,000 or so, because there is some overhead cost with it. But after that, it starts winning tremendously. These other results are really just existence results. They're not anything implementable unless you have matrices of size number of atoms in the universe. And then, they were giddy, so they made this astounding conjecture that it's almost as easy to multiply matrices as it is to add them together. And then nothing happened for a while. And then there was some very small progress that continues to be being made, but it's in, the third digit, very small. So I want to approach this question. So first of all, let me say my instinct is that we should try and disprove the conjecture since everyone else is trying to prove it. And since my training is in geometry, I would like to transform this question to question in geometry and try to approach it that way. And fortunately for me, that the preliminary work had already been done by Strawson himself. So matrix multiplication eats a matrix, eats a second matrix, spits out a third, and it's bilinear. Or you could view it as a trilinear map, which would be maybe better because you're being less biased between your 3 spaces. And when you view it as a tensor, space of trilinear maps, well, if you're already bored, which some of you are, you can try and prove that it becomes, you just take E3 matrices and spit out the trace of their product. Right, so a little bit of language. A tensor, like a matrix, has rank 1 if it's a product of a row vector, column vector, and let's say a vector sticking out the blackboard. And the rank 1 tensors essentially correspond to bilinear maps that can be computed just using one scalar multiplication. Any questions on this definition? First slide with any content. So the rank is the smallest r, such that your tensor can be written as a sum of r rank 1 tensors. And it's essentially the number of scalar multiplications needed to compute the corresponding bilinear map. And the point is that tensor rank governs the asymptotic complexity of matrix multiplication. You can recover the exponent from it. Oh, let me define the exponent. This is the growth of the complexity of multiplying matrices. And classically, you get at most 3. Strawson's algorithm gives at most 2.81, and the astounding conjecture that is that it's 2. Right. So let's start thinking about geometry. So think of this curve as a curve in high dimensional space, and it's the set of tensors of rank 1. Well, that's not really a curve, it's higher dimensional, but the dimension of the ambient space is like capital N cubed, and the set of rank 1 tensors is like 3n. So as if it were a curve, its codimension is so enormous. And a tensor has rank at most 2 if it's on a secant line to the set of tensors of rank 1. And so this conjecture is about a point, the matrix multiplication tensor, whether or not it lies on a secant R plane to the set of tensors of rank 1. So we have a purely geometric formulation now. We have a stratification of our space, and we want to know which stratum our point of interest lies on. So let's view this in a wider context. So I like to work over complex numbers, and I like to work in projective space. Both of these are because I'm lazy. Polynomial over complex number has solutions. Projective space is compact. So I have a projective variety, just a zero set of a collection of homogeneous polynomials. In our case, the variety is the rank 1 tensors, also called the Segre variety. And we're stratifying, but for now, X can be any projective variety. We get a stratification by varieties. Now, it's slightly different than what I said before, because now I'm going to take Zariski closure of points on spans, but that's okay. If I'm going for lower bounds, this is legitimate, but in fact, Bini even proved that it's legitimate for upper bounds as well, which is a little more subtle. And these have been studied for a long time, especially around the early 1900s. It was a hot topic, and had they asked Terracini at the time, he could have predicted Strawson's discovery, because the 7th secant variety, the things that can be the bilinear maps that can be computed with 7 multiplications or 7 multiplications with an epsilon, fills the ambient space. So no matter what bilinear map you have, you should be able to, in that space, you should be able to get away with 7 or 7 with an epsilon. All right, so I want to disprove this thing. So let's let sigma r denote this one of these stratum, and then find a polynomial in its ideal, and then show that that doesn't vanish on matrix multiplication. Pretty simple strategy. And when I entered the business, I thought it was a little embarrassing that even it was not known whether the 7 was optimal. Perhaps that point of 2 by 2 matrix multiplication lied on the 6th secant variety, not on the 7th. Well, as I've been learning, I'm trying to learn some computational complexity, and the sort of standard text that I've been learning from is Arora and Barak. And chapter 14 of their book is called, Lower Bounds or Complexity Theories, Waterloo. So maybe it's not that embarrassing after all. Any questions? Right, so how are we going to find polynomials? Well, there's not a whole lot of polynomials that we understand geometrically. One of them is how to compute rank of a matrix. Matrix has rank R of all of its size, R plus 1 minus 0. And you can use that to get some classical information, but not very interesting. And so what we try to do is imitate this idea of rank method by taking our tensor space and embedding it into a matrix space, and then take minors. So with Ottaviani, we found an interesting one. I'll explain that interesting one in a minute, but just to give you a very explicit realization. And okay, so Strawson had some non-trivial lower bounds, which can be reinterpreted in this way. And he went from the trivial bound of n squared to 3/2 n squared in 1983. And then the advisor hits a home run, the student goes to second base for free. So a student got an error term better. And then nothing happened for almost 20 years. And then with this embedding we used, we went from 3/2 to 2. And that was considered is still considered an accomplishment. So let me explain how we found it, because we didn't just sort of scratch our heads and look for stuff. Anytime you have a vector space V that's acted on by a reductive group, so it's a G module, you can look at equivariant embeddings of your vector space into a space of matrices. And if you have a nice group like we do, we could actually list all possible equivariant embeddings into spaces of matrices. The idea being, if there's a good embedding, it should respect the geometry of the problem. And so even though what we wrote down was quite simple in hindsight, it came after doing the first paper we wrote on the subject did not have that, and it was filled with Young diagrams and all kinds of inclusions of Young diagrams. And the first few we found were far less efficient than the simple one. But actually, if you know some algebraic geometry, the simple one would be the first thing you'd think of, because it's the Kazul complex. So anyway, we were going via representation theory, but you could go via algebraic geometry. And we found these polynomials that exploited the symmetry of our stratification of our space. Questions? Very quiet audience. I don't know why that is. They normally expect, okay. I should have given a chalk talk, I guess. That's the problem. All right. So, but then just a few years later in both algebraic geometry and right here at the Institute, they proved that the game is essentially over for this kind of method. It's not going to take you much further. And we know precisely the theoretical limit, and we know the practical limit now. So we're out of luck. So if you know some algebraic geometry, if you look inside the Hilbert scheme of points, and you have a small number of points, every element of the Hilbert scheme is a limit of 7 distinct points, or 6 distinct points, I guess, or 7, yeah, up to 7 points. Everything is a limit of 7 points, but once you go to 8 and beyond, you have this problem of uninvited guests in your Hilbert scheme. And we now understand why there's this problem with determinantal methods because they're detecting whether our point is in the span of a zero-dimensional scheme of length R, and what we want is our point to be in the span of a zero-dimensional smoothable scheme of length R. So let's make some definitions. So this object we've been studying, which had a very nice, simple, elementary description, now I give you this obnoxious, fancy description to enable comparison with this so-called cactus variety, which is basically the same thing. You look at zero-dimensional schemes of length R that are contained in this case, the Segre variety. And on the top, you want smoothable, and in the bottom, you drop the smoothability hypothesis. And the problem, as I said, is determinantal equations or equations for this larger geometric object. So we have two different stratifications of our ambient space. And the one we care about for complexity theory doesn't fill the ambient space until like m squared over 3 if A, B, and C are vector spaces of dimension m. But this other one fills at 6m. So any determinantal equation is just game over at 6m absolutely and practically much earlier. By now there should certainly be questions because I kind of upped the ante on the talk a little. No, everybody's just okay. Sorry? They're both, they are subvariety. So we have a just any variety X in a projective space. And then we have its cactus variety lives in the same projective space. And we have the secant variety that lives in the same projective space. And this is what we were talking about. And the points on this variety are points in the span of R points on our original variety or in the Zariski closure of such. Here, we don't just take R distinct points. We allow ourselves zero-dimensional subschemes of our original variety and then take a point in its span. And so we're still in the same ambient projective space. And both of these, as you increase R, you eventually fill out your ambient space, but the cactus one fills out much faster than the secant, which is why we're out of luck. And so it's this problem of uninvited guests. And so let's see what we could do to get rid of our uninvited guests. Other questions? Okay. So first thing is we have this beautiful stratification of our space by varieties invariant by a large group action, but we're not interested in an arbitrary point in our ambient space. We're interested in a very special point, and that point also has a group associated to it. So for any tensor, you can just look at its symmetry group. You could define symmetry group of any time you have a variety X that's invariant under reductive group G, you can do for any point in the vector space V, that'll be a V will be a G module, hopefully. And then you could make the same definition, but I'll just restrict to our case in complexity theory. And we look at the changes of bases that preserve our tensor. And so for matrix multiplication, you have a very nice symmetry group. So A is Cn squared, and so is B and C. And you have 3 copies of GLN that preserve your tensor. Namely, if you have 3 n by n invertible matrices, you can do this to your 3 things you eat, and the answer won't change transparently. Right. So now we're going to, since Mateusz invited me, I thought we should talk a little bit about joint work. We had like the most depressing theorem I've ever been involved with ever. This I call our Pyrrhic victory. So, so let's think about what it means for something to be in this R secant variety. This R bar is the tells us. So yeah. So R bar of T is the smallest R such that T is in this R secant variety. And so if the, and that's called the border rank in complexity theory. And so we want to sort of use a little bit more geometry and representation theory. So if we have a tensor border rank at most R, that means we have a curve in the Grassmannian of R planes such that when T is not equal to 0, our R plane is spanned by R rank 1 tensors. And in the limit, the point we care about, T, is in the limiting R plane. And now if we have one such curve and our tensor has non-trivial symmetry, we get a bunch of them. We get a lot because we could just act on it by our group. And this led us to what we call the border substitution method. And now, yeah, you need to know we're using Borel fixed point theorem. So we're not going to use our whole group. We're going to take a Borel subgroup. So in this case, it's just the triples of upper triangular n by n matrices. And the point is, since that's a solvable group, anytime it acts on a space, in particular the Grassmannian here, there'll be Borel fixed points. So this is this special thing, this special semester is about torus fixed points. So here I have a slightly larger group, so my world is even better. Yeah, so that means that if you can restrict to all Borel fixed hyperplanes, we can upgrade a classical theorem to say that we can reduce our tensor problem to a tensor in one dimension smaller, and we can keep doing this for a while as long as our groups hold out and keep helping us. And this use of the Borel fixed point theorem, well, so it's still 2n squared in the front, but now we're down to log n instead of n. And it was so depressing because we knew this was the end of the line for our techniques. And we thought, I was thinking it's time to start looking for a different question to work on. Yeah, that too is because of this thing, really. Because, yeah, so that too, well, who knows? Tomorrow we could decide the actual answer is 2n squared minus 1. But I think most people would bet against that. But there's no evidence that that it is greater than 2n squared minus 1. I'll get to that in a little bit. No, this last step was a desperate gasp to use a little bit of extra symmetry. So what I did was I reduced my problem to a smaller problem. Now, if I could reduce all the way down to 7, then I would have gotten rid of the problem because then the two coincide when r is less than or equal to 7. But say for the question I'm going to be most interested in later in this talk, I'm very far from 7. And so I get down a little bit, but it's not enough to take me to the good range where the Hilbert scheme behaves as if we wished it did. So that's why this is really going to be game over. But yeah, so the punchline is though, this miserable theorem that got me so depressed actually has opened the door because it's this Borel fixed point theorem seems to be worth its weight in gold. So so you're going to be able to object one more time in this talk, and then I'll actually start bridging this gap at the very end of the talk. So please object again when you realize that you should be objecting. So the big change in algebraic geometry in the 20th century was the refocusing on the ideal rather than the geometric object. And so we were looking at the curve and the Grassmannian, but actually, these are points at each moment of time. They define a zero-dimensional smooth scheme. And so we could look at this curve of ideals, and that gives much more information. I was just looking at the ideal in degree 1. Now I can look at the ideal in all degrees. In fact, I have polynomials in 3 sets of variables, so I can look at polynomials in 3 different multi-degrees. I have Z3 graded polynomials, so I have a lot more information. I have a lot of Grassmannians to play with now. And this gave rise to what they call the border apolarity method. So say we had this tensor was a limit of tensors of rank R. I take at each moment in time the ideal of those tensors, of those points, and I consider the limiting ideal. Now here we have another sort of unpleasant fact to face. Because in this business, we really want to take that limiting R plane. But if you work inside the usual Hilbert scheme, the beauty of the usual Hilbert scheme is you have this Hilbert-Mumford regularity. So it says that in order to understand a saturated ideal, you just need to look at the ideal in some sufficiently high degree that contains all the information you need to know. You're working in one, perhaps big Grassmannian, but who cares? And you're doing your geometry as some schemes of some fixed Grassmannian. Everything is good, right? But we're in a much worse situation here because we have to allow ourselves to look at these limiting R planes. That R plane has to stay in R plane in low degree, which is not the case that you get in the usual Hilbert scheme. So you have to work in something called the Heyman-Sternfels multigraded Hilbert scheme. And now we have an even worse problem of uninvited guests. So the usual Hilbert scheme, you fix a Hilbert polynomial, and then you look at all varieties or schemes with that Hilbert polynomial. But here we need to fix a Hilbert function. And in fact, since we have polynomials in 3 sets of variables, we have a Z3 graded Hilbert function. And now we need to work in a product of many Grassmannians to make this thing work. We need to go from degree 1 up to degree of Hilbert-Mumford regularity. So it's a much larger, less controlled space that we're dealing with. And now we have a second. So we first had our uninvited guests in the usual Hilbert scheme, the ones that corresponded to zero-dimensional schemes that were not limits of R distinct points. And now we have these ideals. See, the ideals in this Heyman-Sternfels Hilbert scheme need not be saturated. So now, instead of one problem, we have two problems. We have the problem of smoothability, but we even have the problem of being a limit of saturated ideals. But we still have the Borel fixed point theorem. So, okay, we have more problems, but we have more things to work with. So let's get to work. Yeah, so this is what I was saying. So for each I, j, k, we have a curve in a Grassmannian, going up to the regularity. And all these things have to satisfy all kinds of compatibility conditions. It still has to be an ideal. In other words, you multiply a polynomial in the ideal by another polynomial, you had better stay in the ideal. Yet notice that we fixed the Hilbert function to be constant equal to R after the trivial range. And so you get some compatibility conditions for any candidates in low degree. And the upshot is, if you're not concerned with smoothability, you're not concerned with saturability, you get all winning ideals from this point of view, from the Heyman-Sternfels point of view, or there are none, because maybe there's nothing that's Borel fixed, and then that is a winning candidate, and then you've proven a lower bound. So let's see. This paper finally got published. So previously, this problem had only been solved for 2x2 matrix multiplication. So then we solved it. Well, your matrices don't have to be square. They could be rectangular. So let's go up as slowly as we can. So we were able to solve the next case. Oops. And the case after that. And not only that, there was a real bonus and sort of a relief to me, because we actually had two proofs that the border rank of this 2x2 matrix multiplication was 7 and not 6. And they were both horrible. And one was horrible because it involves this like really ugly differential geometric calculations. The other was horrible because it could only be verified by a computer, because it was using representation theory. But as I learned, polynomials of degree 18 and 64 variables, even if they're highest weight vectors, are not such pleasant objects. So anyway, this new thing, now you can have a handwritten proof that takes half a page to prove the 2x2x2 case. And so that's quite nice. And now let's go to 3x3 matrix multiplication. So Strawson proved 14. With Ottaviani, we proved 15. With Mateusz, we proved at least 16. And we got one more. So again, it's a little embarrassing. We got all this new fancy machinery. It only took us one step further. By the way, the known upper bound is 20. So, if, these things, between Ottaviani and Michałek and this latest, they were a few years apart each. So, maybe in 15 years from now. But anyway, yeah, and the other interesting thing about these methods is they work in regimes that nothing worked in before. If you had a tensor where one of the factors was much larger than the other two, there was no techniques whatsoever available. And these techniques worked, and we were able to prove the first sort of non-trivial bounds for those. And also, it's good for some other tensors, including the 3x3 determinant considered as a tensor, which, if you come to this afternoon's talk, there's some that's actually important for proving upper bounds in this problem. And this afternoon, I'm going to talk about how to use geometry, more specifically commutative algebra and representation theory, to try and prove upper bounds. But let's finish this talk first. Oh, yeah, it's even on the slide. Even this afternoon's lecture is on the slide. Yeah, I came prepared. All right, so now you should have objected, right? Because what does it mean? What are you testing when you're testing that your multiplication map in the ideal does not make the ideal grow too fast? That's a rank condition on your multiplication map. So despite the fact that we could go quite a bit further, we did not cross this barrier yet. And but even the first time they defined it, they knew that now we have a tool for overcoming the barrier, because we're working on a Hilbert scheme, not your normal friendly one, but you still have deformation theory. Even before that, we did some little thing. Maybe I won't dwell on that, but we proved something. The only important thing about this is that the computer scientists wanted to know the border rank of this tensor since 1988. They were asking about it, and we finally solved it in 2020 using sort of a little bit of augmentation of the equations that was not subject to the barrier, but was not going to take us much further. Yeah, so that's what I was mumbling about this afternoon. All right, so the new news is we're implementing deformation theory, and this is work with Manduk and Connor, which should be hopefully on the board. Oh, yeah. So before that, in our old paper, we actually, the reason we did not prove lower bound 18 is because we found ideals that passed all those tests for border rank 17. And it's a list, but it wasn't that long of a list, but we're stuck. And so now, yeah, this work in progress with Connor and Manduk is we've eliminated many of them using deformation theory. So some of them we were able to eliminate because they were not even deformable to a saturated ideal in the appropriate Hilbert scheme. And others were eliminating in the traditional old-fashioned way that you're proving you're not in the principal component. Now, these deformation theoretic techniques, well, what's the only, usually the only thing people know how to do on the Hilbert scheme is compute tangent spaces. But we're dealing with Borel fixed points, so that's kind of bad news because those tend to be the most singular points in the Hilbert scheme. So your naive off-the-shelf tangent space calculation is not going to take you very far because you're working at a singular point, so it's going to have a large tangent space. But we don't just have an ideal. We have a Z3 graded ideal, and we can crush that down to get rid of, just project away one set of variables. And then the ideal starts looking a little bit more generic. And you can do tangent space calculation in these reduced situations. And that, I have to say, it really surprised me that that is working. And we've eliminated a lot of this list. And maybe a few months from now, we'll be done. But stay tuned. And thanks for your attention.
Thank you. Hello, are there questions? So I have a question because you said that some of them were not saturated on the last slide, so I assume some of them were.
No. None of the Borel, if you have a Borel fixed ideal, the odds of it being saturated is really, really small because we've got a nice big Borel subgroup. It's destroying everything it can. So, but some of them cannot be deformed to a saturated ideal. Some of them can. So if you can prove that your ideal cannot be deformed to a saturated ideal, then you know this is garbage for the problem we care about, and we throw it away, and we have one less candidate. Once you prove that it can be deformed to a saturated ideal, then you must try to prove, and we're kind of betting that the 17 is not the correct answer, but if it were, then we'd be at 2n squared minus 1 for both n equals 2 and 3, and I would, if it turns out to be 17, then I would make a ridiculous conjecture, but it's not going to. Because this new methods are only a few months, we've been only implementing them for the last few months. And this quantum book you see there, that killed my research for a year. So that also slowed things down quite a bit. So
my question was going in the direction, can we use it as something positive to find a scheme to prove low cactus one? Can this method be used in such?
Sure, if you can prove that your ideal is, well, they call it saturable, but that's a little confusing. But let's use the Yelyshev-Monduk terminology. So they use the word saturable if the ideal is a limit of saturated ideals. And if you can prove it's saturable, then you've proved that an upper bound on its cactus border rank.
In this case, no, like cactus rank.
In this case, we don't know because some of them are saturable. And now we're trying to prove that they're, oh, I see, but yeah, you only need one. Well, I need to be careful because, so let me say the answer in principle to your question is yes. I'm not sure if our computations give a definitive answer to your question in this particular situation. That would be, because nothing is written down yet. It's all sort of, you know, this. So once everything gets written down carefully, we will be able to answer your question for this problem. Yeah. Somebody wrote down an explicit, yeah. So for a long time it was 21. And then a few years ago, this Russian guy Smirnov, he does this as his hobby. He's, as far as I know, he's not a professional mathematician. He works just with his laptop. And I emailed him because he published this paper, and all it is these very explicit descriptions of curves. And I said, well, how do you do this? And he goes, oh, I do this, I do that. It's my hobby. And then he went into this long discussion about mystical things and the heart of a nation and all kinds of things. So I wasn't able to extract anything particular from him. But anyway, my former student Austin Connor can replicate all of his results. So, because it's very hard to check his results because of the way he presents them. So it was easier for Austin to just reprove them and find new things in the ranges he found. And so there's now several existing very explicit border rank 20 decompositions. That is, these curves of 20 points crashing into each other. That gives an answer. And no one has been able to find one with 19. And I suspect if someone could, it would be Austin Connor, because he's rather, Mateusz can tell you he's rather talented with these kind of things. Yeah.
There are also this now new, those AI techniques.
The AI techniques have done nothing. And we have to turn off the microphone and the Zoom. If I could, I will tell you precisely the nothing that it's done, but that's the short answer, yeah.